how we can improve the formalization of them, so we capture previous constructions and kind of improve some efficiency for some known constructions. So we start from what was already there and we build on top of those. So first, what are vector commitments? So if we have a long vector, we can commit to it in a very concise way. So we put it here in a box. And what this allows later is to open, but not to open the entire vector necessarily, but we can open one position of the vector. So the value in position 6 here, we can open it by giving a very short proof that anyone can publicly verify with respect to the initial commitment. So they will be convinced that V6 was indeed committed in this long vector in the position 6. They were first introduced by Dario Catalano and Dario Fiore, in this paper that formalized them for the first time. And then the new flavors of vector commitment started appearing in the literature, and some of them were extending this opening capacity. So we can consider vector commitments that allow to open a subvector, so more than one position. Let's say 2 positions here, 1 and 6. So we can give 2 values, V1 and V6, and convince anyone with some verification key that those are the ones that were committed in the large vector here in the commit. Other flavor of vector commitments are functional vector commitments, which are even more expressive. So at the opening, we can convince someone that we know a function of a vector. Yeah, I will explain later what kind of function we know for now. So we can have a proof for f of v here, where v was committed in the initial commit. So what we know so far with standard techniques is how to build linear map of vector commitments. And those are defined for functions that look like this. They go from some field to the power n to some field to the power l. And this is a linear map. So it's linear in all the coefficients. Okay. And one particular case of linear maps are inner products, which are very, very useful functionality in many applications. And I define it for 2 vectors, A and B. So an inner product for a committed vector A with a public vector B that defines the function f of B is actually a linear map, but from the vectors of length n to one single element, here f to the power 1. So if A and B are vectors of length n, we can commit to A, and we can open the inner product between A and a public vector B, which defines this f of B function. Okay, so we will focus on this kind of vector commitments in this paper. Also, feel free to interrupt if you have any questions. I may not see the chat, but yeah. So for the motivation, why do we care about such primitives? One simple way to motivate this is to consider the storage delegation scenario. So here, to make it more easy to explain, we have Aladdin that wants to delegate a long vector to the genie, who has a big storage capacity. So Aladdin will commit to the vector in this concise way, and will forget about the whole vector that is delegated now to the genie storage. So later on in time, Aladdin may want to retrieve the value v3 that was in the original vector. So he will query the position 3 and will get the value that was in the position 3 and the proof that indeed this was correctly retrieved from the stored vector. And because of the vector commitment properties, Aladdin can always verify that v3 is the initial value in the vector that was committed in this com, which he stores. Okay, so this proof is concise and allows Aladdin to be convinced that the genie doesn't tamper with his values. And as I said, we can do more than just one single position opening. So we can ask for a function of the vector v that was committed and delegated. And it works exactly the same. Aladdin can just check the claimed value y of the f of v and the proof in order to verify. Okay, so we will like more properties maybe from the vector commitments. This was really basic what we can do in the first place, but we can do more. So let's consider updates. Since the vector can change in time, some position can change, and we already have a commitment for the initial vector, updates allows us to change this commitment into a commitment to the new vector that has this blue v4 here. That in a more efficient way than just recomputing a commitment of the whole vector again. And same updates apply to proofs. So if we already have a proof that position 4 opens to v4, and now we change v4, we can change the proof to a new proof that is correct with respect to the new commitment, and that shows the new value in position 4. And because the initial commitment changes into this blue commitment com prime, also proof for position 2, even if the position 2 didn't change, the old proof is not valid anymore with respect to the new commitment. So updates should allow us to modify the old proof for v2 into a new proof for v2, but for the new commitment where the vector is different, in a more efficient way than recomputing the proof, of course. So those are updates properties that vector commitment are required to have. And also
Anca,
we will ask...
Can I ask a question?
Sure.
So initially you talked about more expressive functions, but here you're only thinking about subvector openings, right?
Yes. Yeah.
So will you tell us about the binding property later? I don't want to jump ahead for something that's more expressive than subvector openings.
Oh, I see what you mean. Like, I don't think I have the formal definition, but
okay.
I
But
can...
intuitively, how would you capture, something like, each opening is consistent with the commitment, but they still form an inconsistent system of linear equations? If I'm just thinking about many inner products, for example.
Yes, that's a very good question, because there are works that really refine this kind of definition. When we talk about inner products and function openings, of course, you can open inconsistently twice, right?
Yeah.
Different position. Our vector commitments and how we define them are extractable. So once you have an opening, you can extract from it a full vector. So this definition just reduces to the fact if there is something inconsistent and you can extract to in two different ways, to two different vectors, then you break some assumption.
I see.
Is this answering the question?
Yeah, it does. I'm still concerned about the size of these proofs and how you might extract, but I'll wait. I think
I think we are in a generic group, like in a algebraic group merger, so we extract. But you have a good point there, because if we don't consider extraction, those definitions may be more involved. And I think there was a paper that just considers assumption, but still reduces this inconsistency of system of equation to some assumption, breaking some assumption.
Okay, sounds good. Another unrelated question. So about these updates, so are we thinking about the party who knows the file as performing these updates? Like, do you have to know the vector and the updates in order to compute the new proofs?
Yeah, that's a great question, because we have different flavors of updating. So some updates need a universal key for for the position, and anyone who knows the new value can update old proof with the opening that is shown in the proof. But there are less flexible updates which need a hint, what we call a hint, and a hint is a proof for the when you update a commitment, you also need a proof for the old opening and a proof of a new opening for this position that changed.
I see.
Yeah, so some are publicly updatable. Anyone who knows the change can take the commitment and update it into a new one. Some need some specific to the change information, which is only computed by the prover. Yeah, in order
I
to
see.
update.
In your file storage example, I presume this is fine, right? You do know the original vector and the update.
Who does the updates, it's simple. But it may be the case we want to update, like Aladdin want to update without knowing all the vector, the commitment. Yeah.
Cool, thanks.
Great. Okay, those are nice questions. So, and also let me they reveal that I just omitted so many things, so I may fix this presentation. So the aggregation. If we have proofs for different openings, we can later aggregate them together into like a concise proof for those openings together. So instead of giving to the verifier many proofs each for each opening, we can do them into an aggregated way. And this should verify with respect to the same commit. The aggregation is, as we discussed for the updates, in this case, the aggregation should be some public operation. So anyone without knowing the entire vector can just take correct proofs of different openings and aggregate them together without knowing the vector. Okay, so updates for the vector. How do you use them in this scenario I was presenting? Probably obvious. If Aladdin wants to update V4, then he is able, if the update keys are right there and it's not a hint update, just to compute a commitment to the new vector. And also the Genie can compute a new proof for the openings that he had already. If he had already opening proof for V3, he needs to update it in a very efficient way. Okay. For the aggregation, if it happens that the Genie already computed V1, a proof for V1 and a proof for V3, and later on he's queried 1 and 3 together, he doesn't need to recompute a subvector opening, which is expensive. He can just run an aggregation, which will be linear in the number of positions he aggregates. So this is way more cheaper than just recomputing a subvector openings, and gives the same valid proof for opening V1 and V3 together. So that's the interest of having aggregation. Some drawbacks about the construction that bother us, and we are looking for better ways to construct these vector commitments. So for now, we have nice properties like short proofs for openings. The verifier is constant, like independent in the size of the vector or of the opening. And we have updates in aggregation as I presented them. But all the overhead is on the side of the prover. The prover may be slow because each opening requires to compute, to look at the entire vector, and it's linear in cost in the size of the vector. So one way to overcome this is to have a space-time trade-off for the prover, where in order to gain time when we open, we just store things in advance. We pre-process stuff and we store it as a prover. So an obvious way to do it is just to pre-compute all the proofs offline, and at the moment of someone requiring some position, the proof is just there. So the time is 0 to compute the proof. Same when someone requires a subvector opening, the cost is just aggregating the already computed proofs for those positions. So this is also very cheap compared to computing something linear in the size of the vector. But also space may be expensive. So this trade-off is kind of moving the problem from the time to the space entirely. Even if computation of all proofs may be cheaper than computing them individually, so we have some amortized cost for the computation, the space of storing, the storing requirement is still something that may not be ideal. And something else that bothers here is, let's see how these properties work. So updates, we stored all the proofs. So Gini here has all the proofs, and one position in the vector changes. So the commitment to the vector will change. So as I explained before, all the proofs here will be unvalidated for that. So what this means that all the effort of storing to be more efficient, it's gone. So the Gini has to recompute all the, or to update all the proof, which is still linear in the original size of the vector. So this is expensive to update all the proofs once one position changes. So this trade-off is not ideal. So we will ask something more, a property that was introduced by Nitulescu et al. And is called maintainability, and ask for the updates of all proofs when we update all to be less expensive than updating them individually, significantly less expensive. So ideally, it should cost to update all the proof, it should cost as much as updating one single proof. Yeah, once you store everything. Okay, so that's something we will also focus in this in our paper. And some questions about how to solve this space versus time. So we said that we require sublinear space and fast updates. And ideally, we would like to be able to change this trade-off at any point in time. So to tune how much space we dedicate and how much time we want to use in the online phase. And for time, it's good to be sublinear in the size of the vector when we are online, when we give the proofs. But ideally, we would like to be even sublinear in the opening size, because sometimes the subvector we want to open is big and or the function is big. So let's go to our constructions.
Can I just ask about maintainability? So
yes.
What exactly is the definition of maintainability, that you should be able to update proofs in time little of the length of the vector, or does it already talk about time-space trade-off?
It talks about how to update all proofs. Yeah, as you said in the first. So updating all proofs should be sublinear in the size of the vector.
So anything that is like a Merkle tree construction is already maintainable, right?
Exactly. Yeah. Okay. I will talk about that. Yeah.
You'll talk about it. Okay.
Yeah. That's the idea we have for now of how to build maintainability in vector commitments. So now that we see the challenges and what were the kind of questions to solve here, let's see our contributions to this. So we first gave a framework to add these properties to any functional vector commitment. So these homomorphic linear map vector commitments, which were defined in general as a functional vector commitment and didn't have updates or aggregation, because they were not considered vector commitments exactly in the original definition. And we have this updatability with static keys, and we define some more powerful aggregation, which is unbounded. We can aggregate even aggregated proofs. We have new simple construction for inner product vector commitments. Some special subset openings in a more efficient way than just aggregating. And this maintainable tree-based construction that works for any vector commitment, so underlying vector commitments with some homomorphic property. And then I will talk about the trade-offs, which are flexible, as I said, like we can tune the space and the time. And what's nice about our construction, because we focus to be as practical as we can, so they can be deployed right now. It's something important for us, is that they use some same setup that some snarks use, and those setups are already available in practice. They were run in ceremonies to generate them. Okay, so let's go to the definition of the algorithms for the vector commitment. So we have a key generation that takes the size of the vector and the security parameter and has a commitment key and a verification key. Then in order to commit, you need the commitment key and the vector, and you can generate a commitment and some auxiliary information, which is usually the opening information. So if it's a binding and hiding commitment, then auxiliary information should contain also the randomness to hide, we will only look at binding commitments without hiding. And to open, we get the commitment key, so this is still a public operation, the auxiliary information, that may be the whole vector, a function, and the claim value, y. And this is the proof that the claim value y is an opening with respect to an initial vector committed in C. Maybe I go the relation, yeah. F of v equals y, and also v was committed in C. So the verification, we'll take the verification key, that may be the same as commitment key, the commitment, the function, and the claim value y, and some proof. And we'll just check if this is correct or not. Okay. So for inner product, as I said, we defined a function applied on the vector A by a vector B, which is the inner product between A and B. A was committed and B is some public function, public vector, which defines the function. And another key strategy in order to define vector commitments is to encode them as polynomials, and then either use some polynomial commitment that's already there, either define some special properties and allow to open in a succinct way. So let's see two different encodings of a vector into a polynomial. It's writing them in a monomial basis or a Lagrange basis. So monomial basis are those monomials x to the y. So any vector can be written as a polynomial by classically looking at the vector values as coefficient of the polynomial. So I have a shift of the power here. Maybe this is bothering for some, but that's the notation we use in the paper. And in the Lagrangian basis, we have a way to write any vector as a linear combination of these Lagrangian polynomials with the coefficient, the values in the vector. And this is interesting because it gives some nice properties when you evaluate polynomials. So we look at this Lagrangian polynomial, and this Li evaluated in I gives 1 and evaluated in G gives 0. So if we evaluate it in anything different from Y, it gives 0. So A of 1 equals exactly the first value of the vector, A of 2 equals the second value, and so on. So when we evaluate this polynomial, as we know, K to KZG polynomials, we simply open one value in the vector. But this monomial basis doesn't have this property, but has other interesting properties we can use for vector commitments. So I will explain how it works for inner products to open a vector which is committed in a form of polynomial in a monomial basis. Okay. Just a short background reminder. We need to know what bilinear groups are. So these are our notation. If A is in brackets with 1 is in G1 and B brackets with 2 is in G2. And we have the bilinear map between these cyclic groups G1 and G2 with values in GT. That has the interesting property that when you pair A from group 1 with B from group 2, we fall into an element from GT that has order AB. G2, that is G2AB. And this is the bracket notation I will use, which is an additive notation. So the key generation will give a commitment key in our construction, which is just consecutive powers of some value, secret value tau, encoded in G1, in the first group. Okay, how do we commit to a vector A? We just write A as I explained. We put A as coefficient into a polynomial, and we evaluate homomorphically, because we don't know tau, but we know tau in the first group. We evaluate homomorphically the polynomial A of x in the value tau in the first group. Okay, so I remind you that A of x is this polynomial defined by the vector. And because this are linear operation and this is bilinear group, we can always evaluate it. Okay, how do we open? So we want to open the inner product between A and B, which is claimed to be the value y, and to prove that this opening is good. So we will give three polynomials evaluated in tau that come from the following computation we do. So, so if we have a of x written like that, we will define a polynomial b of x, which will take the elements in vector b and encode them into a polynomial, but in the reverse order. So bn will be the coefficient for the free term, bn minus 1 will be the coefficient for x, and so on. So if we look at a and b, they are like encoded in a like reverse order in a polynomial, in a monomial basis. So what happens when we do the convolution, like when we multiply polynomial b of x with a of x? The inner product between vector a and b will show out in the power x to n minus 1, because bn will be paired with an here in x minus 1, bn minus 1 will be with an minus 1, and so on. Okay. So we have this, but we have a bunch of other terms in this product polynomial which we want to show that we know. So all the other remaining terms that have powers x to the n or higher will show up as a polynomial h of x times x to the n, right? And all the powers that have inferior, all the other terms that have inferior power to x to the n minus 1 will show us as a reminder. So this is a polynomial that has, okay, sorry, I'm going ahead. This has degree n minus 2, right? But we know that given the commitment key, we can compute polynomial to evaluate polynomial up to power x n minus 1, up to n minus 1 power. So we will define a new polynomial as a degree check to make sure that R has a degree less than n minus 2. Then we will define this new polynomial R hat that has degree at most n minus 1. And we are sure that this is the case because this is our commitment key and all that we are allowed to evaluate. Okay. Okay, I hope this is clear. So now for the verification.
Can you repeat what is HX? HX?
The checks for the verification?
Yeah, your convolution equation AX BX.
Mm-hmm. Yes.
What is HX?
So we know that like when we multiply a and b polynomial here, we will get the y value times x to n minus 1 plus some polynomial times x to n. And this polynomial is part of our proof. We have to prove that the decomposition of a times b in terms of polynomial looks like this. So we have to provide to the verifier h encoded in group 1, r encoded in group 1. But this is not sufficient because R can go 1 power further because of how our setup looks. So we need the degree check. And this is done by defining an R of x, which is x times R, and which will ensure us that we go up to n minus 1, right?
Yeah.
Yes, so those are the checks the verifier should do in terms of polynomial, but of course, they will do it only by checking the values evaluated in tau in using the bilinear map, using the pairing. So I rewrote these checks in terms of bilinear pairings. Okay, so what is the verification key then? The verification key should allow the verifier to check this to compute this second part here, the polynomial b evaluated in tau in the second group. in order to pair it with the A of tau, which is the commitment to A. And also it needs to have this tau to power n in the second group. So these are all the elements verification, the verification key should provide. Okay, oh, sorry. Okay, so as I said, we do the checks here for the degree check and for the inner product. So now how we get to linear map in general here, like inner products are for Fn to F, and linear maps are from Fn to Fl, for any L. So there is like just you can see it as a function, many inner products. So we show a framework to aggregate proofs for inner products here for many BIs into a proof that will be for this linear map. So for this, we need to have inner product vector commitment that is homomorphic, so it allows for this kind of aggregation. And everything goes the same. And we will just check the proof for the aggregation.
The aggregated proof should not, the size of it should not scale with L. Is that the point?
Exactly, yeah. This is a constant size proof. Yeah, showing many values, showing all the vector y as opening. Mm-hmm. Yeah, exactly. And we have some other observations and nice openings for subsets that satisfy some properties. So for this monomial basis, we remark that you can open any range subvector, like range, I'm meaning that from one value k to k plus 1 or to k plus m in the vector in a succinct way, at the same cost as opening one value. So the observation is like same commitment as before, of course, and we will define B of x as in the inner product as xn minus k. And when we do the inner product between A of x and B of x, those consecutive ak plus 1 and ak plus m will show up into these powers of x. And we will have, as before, a polynomial h of x multiplied by x to n plus m, all the following powers, and the reminder that at all the previous powers up to n minus 1 here. So what you need to open is just show the values in red here, aka k to the m, k plus m, and then show the polynomials h of x evaluated in the first group and r of x evaluated in the first group, and of course also degree check that I have to add it here, right? So that's a nice observation because this cost exactly, and we have the same for Lagrangian basis. I will not get into the construction for Lagrange basis, which is more similar to polynomial commitments, classical polynomial commitments with some interesting properties for subvector openings. Let's go to the properties for this kind of constructions we have. So we were interested to have homomorphic construction. Homomorphism can be for commitments. So if we add two commitments for two different vectors, v and w, the resulting commitment, which will not grow in size as in my slides, will be a commitment for the sum of those vectors. Okay. And we have also homomorphism for proofs. So if we have two different proofs for the same commitment to the vector A, but for inner product with B1 and B2, when we add them together, this will give us a proof for the same vector A inner product with B1 plus B2, the two different vectors B here. And a different way to do a homomorphism for the proofs, like this bilinear kind of way, is to have considered two proofs for two different vector commitments for vector A1 and A2, but with the inner product for the same vector B. So we have these two proofs, Z1 and Z2, for these two values. And when we add them together, this will give us a proof for the value Z3, which is the sum of the two vectors and B. And these proofs will verify with respect to the commitment to the vector A1 plus A2. So these are the different flavors of homomorphism. And updatability. So our constructions are also updatable, and how it works. When a vector A will change in a position I by value delta, we will have this update key, which is the same key as the commitment key, and we will be able to update the commitment. Of course, because this is a linear operation, so what means in a monomial basis that this changes means that we have to add the monomial delta times x to the I and evaluate it in tau. So it's very simple. And what happened for the proofs? So the update key for a position I is actually just tau to I. It's only one group element. For the proof, if we already had a proof for A and B, and we want to update AI by the value delta, then the new proof for the new value y prime here will get the old proof and a proof for the canonical vector here, EI, which has one in position I and all zeros, like inner product with B, and this is delta. So we need to compute this proof. We have anything for everything we need to compute it and add it to the old proofs, and this gives us our new proof. Okay, so I think here I give what kind of update proof do we need for such functional updates, for the proof updates. We will need to have all the possible PIs pre-computed if we don't want to compute it on the moment, between canonical vectors EI and EGs, which are 0, and EI or EI, which are 1. So these are just these values which correspond to all the initial update key. It's not quadratic, it's just linear. It's still linear as a update key. Okay. And what about aggregation? So because we have homomorphism for proofs, aggregating different proofs for different values here is just the classical way that we know for other kind of inner product argument constructions, where we pick a randomness and we just compute a random linear combination of these proofs with randomness r to the power 2, r to the power 3 here. And this gives us a new proof, an aggregated proof, which is a random linear combination of the initial proofs. Okay, and we can continue doing this even from our aggregated proof by picking new randomness and computing new proofs, right? Because it's all homomorphic, and this linear combination will give us. Yes.
So where does this randomness come from for the linear combination?
Sorry, can you repeat, please?
Where does the randomness for the linear combination come from? The R?
It's a random oracle. So we need to use a random oracle.
I see.
And both prover can generate it, both verifiers. So we should put in the random oracle input all the claim values and proofs. Yeah.
So this kind of combination seems like it is dependent on how you aggregate it, right? It depends on the order of aggregation. It's not like you just took a bunch of proofs and aggregated.
Exactly. Yeah, that's great question, because this is what I wanted to point out, that before aggregation was one hop and you cannot do it more. And we just did the observation that, yeah, it depends on this tree of how things were aggregated. So we can write, because when you aggregate, you still have to give to the verifier the statement, the claim results. So what if we give them in an ordered way? We give them together with ordered.
So I'm missing something. So if the verifier anyway has to know the order, it has to know the entire set, which makes the verifier linear in the number of proofs you're aggregating, right?
That's not the case, because anyway, the verifier will have to read what are the claims for those proofs.
That's
so
true.
that
Yeah.
any verifier, like that was the argument about this aggregation. The only overhead is that this can now they came in order. Before they were given in any order. Now it's important in which order the verifier reads them in order to check the proof, right? In order to feed them to the random oracle, here the first three, then the result here with the following in the new random oracle, and so on. Yeah, so that's our argument, that the verifier will always be linear in terms of the statement.
Right.
So this will not change anything. Yeah.
Yeah, makes sense. So you're saying it doesn't make sense to think of a verifier who potentially only has, the final statement and the proof and is oblivious to what happened in the past?
If we don't have this unbounded aggregation, that's the case. So we don't care which order those proofs were done, right? You just have, but in the bounded aggregation, the only way we figure out is that the verifier should know the tree of aggregation, how the aggregation happened.
Okay.
That was the question.
Yeah.
Yeah. A way to have a verifier that doesn't depend on this is to have a commitment of the initial one into like some compact way, but that's something we don't know how to do, like to have a commitment of all the output values, right? And to check according to those.
I see. Yeah.
Yeah. And we have a small table just comparing other linear map or subvector commitments with our schemes. There are a bunch of schemes in the literature. These are just a few of them. So what's nice about our construction is that we have this unbounded notion of aggregation, which is like weaker than incremental. Incremental means an aggregation where we can disaggregate smaller proofs from smaller vectors, subvectors from an aggregated proof, and then re-aggregate them together. In our case, you just re-aggregate already aggregated proofs. And cross commitment means that proofs that were committed, proofs for different commitments can be aggregated, right? Not only for the same commitment. Of course, you have to provide all the commitments as input to the verifier. So what we call updates with keyless, maybe this is we have a discussion about what we call keyless. Keyless is if the update is done by the same person that has the commitment key, then there is no need of new key. But what we wanted to say is more like the commitment key is fixed for any value that changes. Okay, so we have this, and what's nice is we can reduce the verification key in our second construction that I didn't present, and we overperform somehow other pairing-based schemes, but of course not in terms of parameters, not the one based on unknown order groups, which is this result here. Okay. So I'll go to maintainable trees for the second part of my talk. And as we already discussed a bit in the beginning, a way to make maintainability is to consider vector commitments that are arranged in a tree. And one simple example is Merkle tree that maybe anyone knows. So let's consider that the leaves here are just the vector or a hash of the vector, a hash of each value of the vector, I want to say. And then we continue completing the tree by hashing each children, like hashing 2 children for each node together. And we do this until we reach a root, which will be our commitment to the whole vector. So this is a way to describe a generic in a more like generalized way, that the commitment to the whole vector is in the top, and then what we have in the tree is commitment to half the vector to the left and half the vector to the right, and we continue like that down to the leaves. Okay, so this allows us to update. If we store such a tree, an update means that if we change this value, we have to recompute all the siblings, all the nodes that were influenced by this value in the computation. And that will update all the others because the others were not affected by the change. So I had a small comparison of the advantages and disadvantages of having the word of pairing-based vector commitment that I presented before, and this tree-based solution that have logarithm size openings, so the proofs is not that concise. They have same logarithmic time verification, and they are not aggregatable. They don't have aggregation in a same nice homomorphic way as we saw for the pairing-based one. The advantage is that we can do these trade-offs by storing part of the trees, which is something that can help more in computation than just store partially the proofs for the pairing-based one. They have transparent setup because they use hash functions in general. The parameters are independent of the size of the vector, which is not the case for the vector commitment I presented, where the commitment key will set a bound on the vector size. And they have this maintainability for proofs. When we store all of them, then we can update them in a very efficient way. Okay, so let's see how we do get the best of both worlds. So the idea is to use the tree-based structure in order to have maintainability, but to put in this tree generic vector commitments, so with some properties. We don't use hash function. We would use some generic vector commitment. So we can also consider any arity, not just two, and we can tune the trade-offs looking at this arity, because we can store m elements and pay log m in size and the prover time, but in the size of the proofs. And this means that you can also update all of them in log m time, which is very efficient. Our construction also uses the same setup as for the leaves, like the building block, which is a vector commitment I presented before, or any other that has same properties. We also have a multivariate polynomial construction, which resembled with something that was known as hyperproofs. Yeah. So we call our construction Muppets. And this is from Maintainability updated tree-based vector commitments. So if we write the length of the vector v as a power of 2, let's say we pad if this is not the case, but we consider for the sake of explanation that we have 2 to m plus k plus 1 length vectors, and we arrange them into a tree in the following way. So we cut them in chunks of 2 to the k length and commit to those vectors. So the leaves is not even the commitment to a single element, it's the commitment to a range of elements in the vector, and we keep going, as I said, in the upper parent of this, there will be a commitment to the concatenation of these vectors. And remark that there is no dependency. You can compute those levels independent, because those are commitments that you can compute independently of the children. So this tree is not as a Merkle tree where you have to hash progressively. Okay, and our vector commitments have depth m for this, which is this m from here, and the proof size is m plus 4. No, it should be, yeah, it's m plus 4, where m is here, it's log from the vector size. And here we have 2 to the m chunks of size to the k, as I said. Okay. So why, how we can prove this? We can prove this by revealing. So if we want to prove V2, which stays here, we have to reveal all the siblings in order to check that the commitment of V is exactly it's coherent with this base commitment. So we can store 2 to the m and open V2. So the prover doesn't have to like recompute all these commitments. It can store them, and we can. Oh, I hear myself. And we can open V2 from C commitment from this commitment at the leaf level. So this means that you compute O2 to the K, the computing this. Okay. So to update all, it means just to recompute the one chunk where the vector changed, proof for that chunk. So if we have a new V2K plus 3, this changes, and we have to recompute all this that are in the siblings and in the path up to the root from that chunk. Okay. And what's the downside of this construction is that the aggregation now needs to use some inner product argument a proof of inner product argument in order to get all the proofs together into an aggregated proof, which is size log Sm for chunks of size for S proofs, and M was the same as before, the depth of the tree, and the verification is in O log Sm. Okay, so I didn't present like in details this, just the results for it. Some future directions and what's there left to be done. So we are still looking into vector commitments that can have transparent setup. We also think that linear maps, it's kind of restricted class of functions. So maybe there is a way to go from this to quadratic openings or some more expressive functions. Also, there may be post-quantum vector commitments with same properties. For now, there is one which is it's the tree base and replacing the hash with some lattice-based hash, kind of, which has nicer properties. There is an argument of knowledge of openings, which we are looking at, just not showing all the openings to the verifier, but just show knowledge of the openings, and the verifier it will not be linear in the size of the openings. And structure preserving vector commitments, this will be interesting to have for the tree structure. So instead of having the parent should be a commitment of the children, but because of our commitments are not structure preserving, they commit to field elements, which are the vector, and the commitment itself is a group element. You cannot commit to a commitment. So it will be very interesting to have structure preserving vector commitment where everything is group elements, for example, and you can keep committing to commitments. And that will lead to similar things as Merkle trees. And then recursivity for the tree-based construction, I think it's the same, of the Merkle tree kind of construction. So that's concluding my talk, and I'm happy to take questions. And if you are interested to work on related problems or these problems, we have grants and more collaboration opportunities on our website, cryptonet.org. So you can go to the grants session. Yeah, thank you.